Fiber optic.
Do we literally need the card, or are you just teasing? Because mine's like buried somewhere in a filing.
Oh, I'm teasing. I'm teasing.
Because I was like, I don't have time for this.
No, get it out like.
In my brain. Okay.
Yes. So I'm going to be testing your certified little card there because I'm going to take it away from you if you can't answer these basic questions. You ready? Basic jargon you guys should know for the test, which you'll be quizzed on, is we have multi-mode and single mode. One's larger, one's smaller. Carl, do you recall the size of either one of those?
0.9 and 125 for the microns.
Yes, 9 micron for what type of cable? Multi-mode or single mode?
Single mode.
Yes.
Yeah, I keep saying 0.9. It's 9. Yeah.
Yeah, it is 9. That's right. You'd see that on the test. I don't think they'd be that mean to put a 0.9 instead of 9, but yeah. And then multi-mode, there's actually 2 sizes there. You recall those?
50 125 and 62.5 125.
Yes. And the 125 that he keeps throwing around, Trevor, what is that referencing? What is that 125 referencing?
I'm not really sure. Kind of forgot.
Oh, take a guess, Trevor. There's a word on this slide. What is 125 referencing? So Carl just pointed out that the core of the fiber is 9 microns for single mode and 62.5 for multi-mode. So what do you think the 125 is referencing? Come on, Trevor, you can do this. Trevor, come on. We're not giving up on you. Let's go.
Is it the cladding?
Yeah, the cladding. Good job. All right. So when we're stripping fiber, Lucretia, see you itching at the bit to answer this one. When we're stripping fiber, what are we stripping off of the fiber in order to connect it or fuse it together? Again, it's a word on this slide.
We're stripping off of the cataline.
What? Are you sure? I didn't quite catch that. What did you say? What are we stripping off of the fiber when we're going to terminate it?
Well, you're getting rid of the buffer.
Yes, you're stripping off the buffer. That's what I thought you said.
That's what I meant.
Oh, right. Yes. Okay.
They were stripping off the cattle.
Yeah,
I mean, I get I'm driving, but I'm pretty sure I heard she's stripping off the cattle.
Yeah, I think she did, or I think her bad internet connection because her husband's using up all the bandwidth. Oh my gosh! All right, let's move on. This is getting crazy. So, since this is the Fiber Optic Association, they like to tout fiber being used everywhere, but typically fiber in a premises network is typically used for the backbone cabling. So the connection between the main cross connect or the computer room and a telecom closet. This is where we're going to see fiber being used. And if I were asked today by a customer to install fiber from one place to another, and they said, we have 62.5 equipment, Silas, but I want you to install fiber. What type of fiber would you install today, Silas?
Single mode.
Single mode. What if they go, we can't use single mode. We have equipment that uses multi-mode. What type of fiber would you install? Huh?
It's okay. I'll install the single mode. Pay the extra money for it.
Anybody got a better answer, Silas? Because you just pissed the customer off. They're like, okay. I'm not paying to upgrade my equipment. I'm using multi-mode equipment right now. But you're correct. You should pull single mode as well. But what specific type of cable should you pull?
Laser optimized.
Laser optimized, which is 50 micron core multi-mode.
You're talking about the hybrid stuff.
Derek says hybrid. Yes, it has both single mode and multi-mode. So you guys are all partially correct. So good job, everybody. Yes, you can install hybrid. So here they're talking about the main reason why you'd want to install an only fiber optic network throughout a whole building and eliminate the need for an HVAC. HVAC is heating and cooling system, and power the hubs and switches is to install a fiber optic network, a passive optical LAN. Passive optical LAN is going to be cheaper because it eliminates the need for, don't go to the next slide, thank you very much. I'm going to fire that assistant. The passive optical LAN is going to require no electricity and no heating and cooling in these telecom closets because they use a splitter, which is passive, doesn't require power. Okay, so that light goes down to individual channels, and that one fiber can feed up to 32 different stations. So that's their thing. Honestly, I've never seen a network like this that is pure fiber. You're going to need a little fiber converter to convert it to an Ethernet because all computers and desktops use Ethernet wired copper patch cords. You need to convert that to electrical signal. So other optical LANs, we have fiber to the home, FTTH. Okay, this requires a NID or some sort of device. It's called a network interface device to be powered to convert that fiber signal into an electrical signal to provide services to customers. So a lot of times you can see in this image here, they need a UPS because if the power goes out, we still want to be able to power this equipment so we can still get services. So this one, fiber to the O, fiber to the office is what they're talking about here. Not a major test question. Passive optical LAN, we just talked about that one. Again, you need a converter or a device at the desktop to convert that fiber signal into an electronic signal. That's what I was talking about. And I think this was the one place that has a passive optical LAN installed at this location right here, which is the San Diego Library. And that's where the FOA was involved with installing a passive optical LAN. But besides that, I don't think it was ever really installed anywhere else. So again, the major benefit here is it's cheaper because it eliminates the need for power and HVAC to the telecommunications closets. Okay, other things, make sure that you're FOA certified. Okay, this is what they're talking about. AC just talking about the FOA certification there. Outside plant or premises, what type of cable is installed outside? Andrew, what type of cable is installed outside?
OS2.
OS2, yes. OS2 is single mode fiber. OS2 is actually better than OS1 because it is a low water peak fiber. And then inside the premises, typically what is installed, Silas? Both.
I'm Caleb's. What did you say?
What type of fiber is installed in the premises?
Single mode.
Single mode and
Multi-mode.
multi-mode, yeah. Right now we're going to be in that in-between phase. So yeah, single mode and multi-mode, but it is becoming more prevalent is single mode. So if you see a test question, it will ask you premises cabling typically uses multi-mode and outside plant uses single mode. Okay, so keep that in mind. That's going to be a test question. Next, why do we not use an OTDR to test a premises network? But for outside plant, where we go several kilometers, we use an OTDR. You guys remember the OTDR reference? I'm going to not pick on any one, but I want you to put that in the back of your head because we're going to come across it here in a minute. So outside plant, we use fusion splicers, the splice connections. You can see there's examples, some of the imagery here. Again, single mode fiber for outside plant installations. Premises cabling, we're going to use typically multi-mode fiber. Okay, and occasionally you will see single mode fiber installed as well. That's becoming more prevalent. So installing fiber Okay, here you can see a fiber switch. Okay, fiber patch panel. Okay, fiber inside of premises in this ladder rack when we're installing fiber. It should be installed inside of the flexible conduit. See this orange flexible conduit here? Okay, that's to keep the fiber protected from other type of cabling that may go along this ladder rack. So we want to make sure that it is protected. It's either in a tray like this one, this yellow tray. Okay, only thing goes in there is fiber, or it should be in a ladder rack. It's going to be installed in a flexible conduit. Sometimes they put the flexible conduit in the tray or the basket, and sometimes they mount it off to the side. So here you can see the orange flexible conduit, and that's where the fiber runs through. Okay, so here you can see it inside the cable tray, and you can see it's kind of getting covered up, and there's some problems getting to it, but anyways, it's still protected. It's not going to get squished by the heavy copper wiring. So premises cable installations, here's some really old pictures of fiber. You can see the little spool up here coming out of the conduit. Okay, that service loop spool. What is the size of that spool? What is the smallest diameter that can be? We have two numbers, 10 times the diameter and 20 times the diameter. What do you think, Michael, Kendall, Michael K?
Is it 10 times installed?
Yes, 10 times the diameter installed. And when you're working with it, when you're pulling it under tension, you want to make sure it stays 20 kilometers, 20 kilometers, 20 times the diameter. All right, so moving on here. So typically, most fiber connections are going to be duplex, full duplex, meaning it's going to use two fibers to communicate. Okay, one fiber to transmit, and it's going to go over to the receive station, and then one to receive from the remote station. Okay, if you're using one fiber, which we have been talking about here in previous slides, okay, we're going to use different channels or different light. Okay, so the wavelength is going to be different for transmit than the wavelength that's going to be used for receive. So here we're using violet to transmit, and then a little bit down the spectrum, we're going to use red, the color red, which is a different spectrum. Again, these colors we can't see with our own eyeballs, but the visual is put here with the different colors just so we can get the idea of using different wavelengths. So media converters, I showed this off in class. Okay, it is a device that is going to convert the electrical signal into light. So this media converter does need to be powered. Okay, small and expensive. This little device is going to convert Ethernet copper signaling to Ethernet fiber light signaling. So how fiber links work? Hey, get back there. So we have the transmitter, which is going to generate the light source. That light source can come from laser. What's another type of light source that multimode typically uses? Jason, Owen, what do you think? Another type of light source besides a laser.
I can't remember off the top of my head.
Anyone else want to tackle that?
Is that infrared?
Infrared is pretty close to the spectrum. It's an LED. So yes, you're pretty darn close there with infrared, but a LED is a light emitting diode. Yeah, so LED is a light source or a laser is a light source. When that light passes through a connector and then down the optical fiber, what is it that happens to that light? Trevor, what happens to the light as it's going through the connector and down the length of the fiber? What's happening to it?
It slowly gets dimmer, not as good of connection.
Yes. Anybody wanna call that a specific term?
Attenuation.
Attenuation is loss. Yeah, good job, everyone. Attenuation. So when it hits a connector, you can see here with the signal, okay, it drops significantly. Not gradually, drops significantly. Why? What is happening at that connector? The other Michael, what do you think?
You want like a specific term? Like, is it just something talking like loss or?
Yeah, so loss is happening, but why? So if you don't have that specific term, then maybe explain why we're having excessive loss.
Because
connector to connector.
I just lost my train of thought. I guess because it's with the connection couldn't be, or it could be dirty, or not properly, I guess, lined up, connected right.
Absolutely, Michael. Yes, that's called where you have excessive reflection. Okay, excessive reflection. That you're just going to have the light's going to either have excessive loss because it's not lined up, or dirt and other things are going to keep it from going through to the other connector. Okay, by the time we get over to the other end, we need to make sure that the amount of errors that we have and the amount of power that we receive is enough that the photo detector can actually detect that there is light there or not. So this is very important. What is it that we plan out ahead of time before we install it? What do we do before we install fiber? We verify what?
It's off.
Say it again, Silas. We do this in the design phase. We do a wireless links, or sorry, a link survey, right? We identify how many connectors, how many splices we're going to have, and we do a link loss survey to figure out how far the cable's going, how much loss we're going to have per kilometer, and that's done in the design phase. Okay, so Andrew mentioned OS2 fiber. OS2 fiber is called low water peak single mode fiber. The whole idea of low water peak single mode fiber is a phenomena happens where our equipment is not able to detect the wavelengths in the between the 1300 nanometer wavelength, because water molecules, water in the air absorbs that wavelength, so we cannot detect it. Okay, so low water peak single mode fiber allows us to reduce the amount of loss, okay, and be able to use more frequency channels, which allows us to have a more dense connection, so we can have more channels. So we use OS2 fiber, okay, low water peak fiber, and that allows us to have less loss, and we can use those channels now for transmitting data and receiving data. So the frequencies that you need to know for multi-mode, we use the lower wavelength, 850 and 1300 nanometer. And for single mode, we use the 1310 all the way up to 1550. Now, answer me this question. Let's see who we're going to have answer me this question. I wonder if Adam can answer while he's driving. Don't crash, Adam. So, where do we have the least amount of loss? Single mode or multi-mode frequencies?
Single mode.
Single mode, we have the least amount of loss. Okay, so the higher the wavelength, the less loss, the less susceptible to loss it is. So we like to test the fiber at the higher frequency wavelength. All right, so the link loss budget, that's what I'm talking about. We're designing our fiber plant. We do this in the design phase before we dig a hole, before we transmit, or before we do any type of digging and installation. So this link loss budget, I'm going to go over this, and then we're going to have a little quiz that I'm going to have you guys put into chat. And I'm going to leave this up for our little break. So we're going to do a quiz right after break. So pay attention. So typical losses. Okay, this slide right here, I would write down because you're going to get a test question that relates to this, and we'll do a little quiz when we come back from break. So if you have multi-mode fiber, you're going to get 3 decibels of loss per kilometer. Okay, so real quick, if I have a 2 kilometers of multi-mode cable in my premises, how much loss can I expect between the transmitter and the receiver, Michael? Michael K this time, sorry. How much loss? So if I have 2 kilometers of cable, how much loss will I have on that cable?
I'm not sure.
So I have 3 decibels per kilometer, and I have 2 kilometers. Multiply them.
3?
3
Wait.
kilometers, sorry, 3 decibels per kilometer. I have 2 kilometers. 3 times 2.
6.
6. Okay, everyone follow that? For every kilometer, I'm going to have 3 decibels of loss. If I have 5 kilometers, Autumn, if I have 5 kilometers of multi-mode fiber, how much loss can I expect?
15.
15. Yay. We can all do basic math. Okay. You got to be able to multiply. You guys can do it. I know it. Okay. That's at 850 nanometer. If I am at a higher wavelength, as Adam pointed out, guess what? I have less loss. Okay. So Carl, if I have a 5 kilometers of multi-mode cable, and I'm using equipment at 1300 nanometers, I have 1 decibel of loss per kilometer. How many decibels can I expect to lose in that 5 kilometers, Carl?
5 decibels.
5 decibels. Nice. Okay, we all got that part, right? Moving on.
No. Can we go over that one again, please?
Sure. Go ahead, Adam.
Sorry, is it just by price? Why would you not always just use the higher, like the 1300 instead of the 850 to decrease your loss?
That is a perfect question. And it is based on price, because equipment that works at the higher wavelength is more expensive. It's harder to detect that wavelength. So yeah, if you can, absolutely use the higher wavelength, but it's not always an option or available when it comes to equipment that we use. All right, so let's go over this one more time. So if I have multi-mode cable transmitting using the 850 nanometer, and I have 1 kilometer of fiber, that is going to have 3 decibels of loss. If I have 2 kilometers, that's 6 decibels of loss. If I have 3 kilometers times 3 decibels per kilometer, 3 times 3 is 9. So these numbers, okay, are going to be nice to know for the exam. I can't guarantee that the problem or the question that you're going to run across is going to provide these numbers for you. But I'm fairly certain, based on what I've seen, that you will be given, it will say, if you have single mode fiber with 1 decibel per kilometer of loss going 10 kilometers, and 2 connectors, how much loss is acceptable? So that would be the question that you would be phrased. So you go 10 kilometers, that's 10 times 1 decibel per kilometer, that's 10 decibels of loss on this 10 kilometer link. Now come down here to connectors. Okay, connectors, 0.3 to 0.75 decibels per loss. It will tell you which one to use. More than likely, it's the 0.75. So that means each connector can have 0.75 decibels of loss. Okay, so if I have 2 connectors, that's 0.75 plus 0.75 equal 1.5. Right, 75 plus 75, you got 75 cents in this hand, 75 cents in this hand. Put it together, you got $1.50. Okay, so 0.75 gives me 1.5 decibels of loss plus my 10 kilometers. That's 11.5 decibels of loss. So the test question will say, if I'm getting 12 decibels of loss, is that an acceptable link? You would say no. It should be under 11.5. Okay, so that's the type of, we're going to take a break. I'm going to leave the slide up and you guys will be able to kind of think through this. Okay, I'm going to give you the length of cable, the wavelength, connectors and splices. And you need to do some math and figure out what is the maximum amount of loss that I can expect to have on my fiber link.
Now, is it always 11.5 or is that just for single mode or?
The 11.5 was I have 10 kilometers. So we're
right. Oh, I got you. That's just for that scenario.
Yes,
after you
that
did
scenario.
Okay.
You got it. So you have 10 kilometers, single mode fiber. That's 1 decibel per kilometer. That's 10. Okay. Now I add in my 2 connectors. 0.75, that's 1.5 plus 10 is 11.5. Cool. Anybody else need any clarification before we take a break?
Nope.
Awesome. I'm going to derive a really complicated example. I'm kidding. It's not going to be too complicated. So when I'm calculating out these problems, they're trying to figure out the max amount of loss. I am going to be looking at the greatest number. So for a single mode and multi-mode, obviously 3 decibels per kilometer, 850, 1 decibel per kilometer at 1300. And when I talk about single mode for the premises, that's going to be 1 decibel of kilometer per kilometer at either wavelength. But when I look at connectors and splices, I want to use the greater of the 2 numbers. These are the official EIA, TIA maximum amount of loss that you can have. So even though it says 0.3, that's what they recommend, but the official standard says you can have up to 0.75 decibels of loss. So use these larger of the 2 numbers. So if I were you, I would take either a screenshot of this slide or write this down. 3 decibels per kilometer, 850, 1 decibel kilometer, 1300 for multi-mode. I'd write down 1 decibel per kilometer for single mode, premises, and OSP or outside plant, 0.4 decibel, 1310, 0.25 at 1550. And then I write down 0.75 connector, 0.3 splice. So if I were you, that's what I'd write down. Here we go. You ready for the first question? As soon as you have your answer, type it into chat.
Are we chatting to everyone or just to you?
To everyone. Well, you make a good point. Do it just to me so we don't give away answers. Nice. Do it just to me. Direct message. Okay? You ready? Here it is. And the first person to get it gets a lollipop or a piece of candy next week. There it is. Got it wrong, Silas. You can't be that fast. Come on. Focus. Do some math.
Is this OSP or is this premises?
Good question. This is not OSP. This is premises. Since this is premises cabling class, that's where we'll focus on. But that is a very good question. So if you want to change your answer, go for it. But this is not outside plant single mode. This is premises. I should have specified that. My bad. All right, I got most of the answers in. Hopefully a couple of you corrected the first answer that you submitted because we were talking about premises cabling. Premises cabling for single mode fiber is 1 decibel per kilometer. So that's 6 decibels plus 2 connectors. That's 1.5 decibels plus 5 splices at 0.3. That's 1.5. That equals 9 decibels of loss. So if you answered 9, you are correct. Again, I apologize for the OSP. It is not outside plant. This is premises cabling, so that's where our focus was. Okay, this next one more problem. You can do this one. This is multi-mode. You got your numbers for multi-mode handy? And by the way, the first person to answer correctly, not the first person to answer, Silas, is Caleb. So Caleb, next week, remind me, you get yourself a free candy bar. Hope you like candy.
Yeah.
All right, good. All right, here we go. Multi-mode. Seeing a lot of correct answers so far. I've only seen one incorrect one. You guys are killing it. That's awesome. All right, here it is. Multi-mode fiber. We have 2 kilometers at 850 nanometers. That's 3 decibels per kilometer. So that gives us, again, 6 decibels for loss because of length. And then we have 2 splices. Okay. Whoops, I got that wrong. 2 splices should be 6 decibels. And then we have 2 connectors, 0.75 plus 0.75. That's, okay, 7.8. Okay, a lot of you did 8.1, which is the correct answer because I accidentally have a wrong slide. Let me fix this slide real quick. Whoa, that's not good. So there's a corrected slide. We have 2 splices. Okay, a splice is 0.3. So 0.3 plus 0.3 is 0.6, plus our 1.5 decibels for the connectors, 2 connectors. That's 8.1 decibels of loss. All right, that's what you got. You guys did great. All right, let's move on. So this fiber optic link or loss and power budget is done during what phase? When do we do this? At what point?
Design.
Yes, love it. Thank you, Autumn. Design phase is when we do this, during the design phase. So let's go over some different components that we need to know and identify in test questions. We have the cable itself. The cable, fiber optic cable, is referring to the protective coating, the strength members, the center reinforcement, okay, the fiberglass rod inside. So these are all part of the cable that protect the fiber. The connector are these things that join fibers, not permanently. They're demountable, meaning we can disconnect and reconnect for changing our plant. So connectors are for reconnecting and connecting. Splices permanently join fibers together. The hardware is referring to the boxes, the breakout box, the patch panels. These are the hardware that protects our connections. Okay, and then the test equipment, which we'll talk about here in the future slides, is how we test and make sure that the fiber that we're installing is going to be adequate for the intended network that we're going to put on it. So cable identification, you're still going to have to be able to identify different types of cable on this exam, even though you already are certified. You need to identify the zip cord. Patch cords, okay, are this first one. Patch cords use zip cords. Whether it's single mode or multi-mode, they still use a zip cord. There's 2 fibers in there. The type buffer distribution. The idea of a distribution cable is it's one cable jacket with multiple fibers inside of it. Then we have a loose tube. Loose tube is the individual fibers are loose inside the tube so they can move back and forth as tension is pulling on the cable jacket. Okay, loose tube. Loose tube is typically used for outside plant installations, by the way. Loose tube is for outside plant. And then we have tight buffer breakout. So a breakout cable, you can see, is a little different than distribution cable because each individual fiber has its own jacket. As opposed to distribution, they're all put into one jacket. So the cool thing about the breakout cable is it does not need a breakout box to protect it. You can put a connector right on the end and plug it into your equipment. You don't need a hardware to mount this in. And again, this diagram you will see on the test. The very center is the core. That's the pure silica. The very center is the core. That's where the light travels down, is the core of the fiber. Trapping the light in the core is the cladding. The cladding is always 125 microns in size for a glass fiber. The cladding traps the light in the core. And then to protect the glass, we have a plastic coating called the buffer. The plastic coating is called the buffer. That's what we strip off of the fiber when we're terminating fiber. Typical colors, okay, for OM1 and OM2, okay, typically is orange. Okay, that is going to be multi-mode fiber. OM3, OM4, which is laser optimized, is typically aqua colored. That's what you see in the image here. Aqua colored jacket is OM3 or OM4. That means that it is a 50 micron core. Okay, single mode is referred to as OS1 or OS2, and that is yellow. So these are the colors you need to know. Orange for multi-mode, aqua for OM3, OM4 multi-mode. Single mode is yellow. You got those three colors down? You're good to go. Which fiber is the first fiber in this aqua colored distribution cable? Brendan, what do you think? The very first fiber that we should terminate in the very first port in the breakout box.
The blue one?
Yeah, the blue one. Let's see if we can get this one. I'm going to ask, let's see if Adam. Oh, by the way, Adam, you get a candy bar as well because you answered the second question correctly. You had the first correct answer. Adam, what is the third color? The third fiber optic port should have what color?
Yellow?
No, in this in this aqua cable, which fiber should be in the third port?
Green.
Yes, green. That's right. Remember, blue, orange, green. Okay. These colors right here are the official order. Okay. The fiber color codes follow the same telecommunications color code that we use for telephone. So the punch down block that have the 25 pairs, okay, these are the color pattern. Blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, aqua. These are the color codes that we follow, the same ones that we follow for the POTS or telephone line. Okay, but you only need to know the first four: blue, orange, green, brown. You got those, you're good to go. Joel, which fiber in which loose tube in this bottom image should be the first fiber connected to the first port in the breakout box?
Not blue.
No. So you have 1, 2, 3, 4 tubes. Each tube has 12 fibers in it. Which fiber should be connected to the first port? Try it again, Joel.
I'm not sure.
Anybody else want to take a stab at it?
Orange.
Nope. What is the first?
Is it blue?
Which blue? Which fiber in the blue tube? Lucretia?
The blue one in the blue tube.
Yes, the blue one in the blue tube is the first fiber. What is the second color, Michael? Michael K., what is the second color that we should terminate in port number 2? Tell me the color of tube and the color of fiber. The second port, the second fiber port should be what colors of fiber should be connected to it?
Orange.
In what tube?
The blue.
Yes, Joel, thank you. The orange fiber in the blue tube is the second port. Let's try this one more time. Jason, what is the fourth port? What color fiber from what tube should be plugged into the fourth port?
In the blue.
Say it again. We missed your first word.
Brown in the blue.
Yeah, we got it. The brown fiber in the blue tube, because the blue tube is the first tube. Okay, I'm going to do one more. And you'll get a candy bar as well. I got to write down all the candy bars I'm giving away. Okay, so who got the first one? It was Caleb, right?
Yeah.
Caleb, and then Adam. Okay, so the first one to put into chat. Actually, no, the first one to speak up verbally. Okay, so get your microphones ready. The first one to speak up. Port number 13. Fiber tube. Tell me.
Blue.
Wrong.
Oh.
Orange blue. Blue.
Blue aqua.
No.
Orange blue.
Yes, orange blue. Was that Carl?
Yep.
Yes.
Yeah.
The orange tube, the blue fiber in the orange tube. Yes. Okay.
I'd like to speak up for Jake McCabe because I think he said that first.
He did?
I think so. I think he just doesn't want to say it.
Jake, did you say it?
Yeah, but apparently I didn't say it loud enough, so.
Oh. All right, Jake. Thank you, Austin. I'm going to bring you one as well because I thought I might have heard it, but I wasn't quite sure. All right. Hoofda. I got 4 candy bars I got to bring next week. All right. Good job, everybody. Let's move on. So how do we choose what fiber we want to use? Of course, money is always going to be the number one, but we want to know where it's going to be installed. If it's going to be installed in the plenum inside of the building, we got to make sure it's plenum rated. The plenum is that air return space above the ceiling. Okay. We got to make sure that we have enough fiber. So we have fiber in case one of the fiber lines breaks during installation. We have a backup fiber. So we want to make sure we double up at least from what we bare minimum need. Okay, and also upgrades. So as Silas pointed out, we want single mode fiber, even though we're only going to use today multi-mode because that's what my equipment supports. I want to be able to upgrade my equipment and have fiber ready to go to meet the needs of high bandwidth. Okay, and then make sure that the hardware is going to be hardware that is specially manufactured for the type of cable that I'm using. Okay, so patch cords, again, that's going to be a zip cord. Short distances are going to be a breakout cable. Okay, if I'm just going from one room to another, but if I'm going longer lengths, I'm going to use distribution cable. Indoor jacket for flammability ratings, I want to make sure I use plenum rated cable. That's OFNP, typically. We'll talk about that on the next slide here. And then indoor-outdoor cabling for campuses. So when I go from one building to another, where the cable's going to be possibly going underground, I'm going to make sure that it's rated for outdoor use as well as indoor. Tensile load, 200 to 500 pounds max when pulling. Temperature range. Okay, did I tell you guys my story about pulling fiber in Las Vegas?
Was it when it got hot up on the roof?
Yeah. Yep. Yeah. So pay attention to temperature. That'll definitely help you. So the OF rating, okay, the optical fiber rating for UL code. If I look at this fiber, up here on top. Okay, and I go, no, 62.5, it's multi-mode. Really good. The UL, type OFNR. What type of fiber? Where can this fiber be installed?
Vertical runs.
Yeah, riser, the R. Look at the last letter in this. OFNR, that is a riser rated. That means it goes inside of a conduit. Vertical runs, rise. Okay, OFNP is plenum rated. These are the two that you need to know. The R is riser, P for plenum. R for riser, P for plenum. There are other ratings, but those are the two that you're going to see on the test question, and two that you're going to be most popular for plenum cabling. So, Silas, you're going to install hybrid fiber, right? Hybrid cable. It has both single mode and multi-mode in it. What if I'm doing an installation in a house and they go, we want fiber in the house, but we also need copper connections? That's where we use composite cable. Honestly, I've never seen copper or composite cabling that has copper in it as well, but it is there. So I guess it's just hard. I can't find it. I want to buy some and I can't find it. So hybrid cable, multi-mode, single mode, and composite cable has copper in it. Composite copper, CO. Different types of connectors. Okay, connectors are demountable, splices are permanent. Let's go over those. These are the connectors you're going to need to identify for the test. Okay, stick and twist. Stick it in, twist it to lock it. Stick and click. You stick it in, it just clicks in. Stick and click. LC, it's little. It's so little. LC is a little ferrule. That little white ceramic part is a lot smaller than STs and SCs. So it's really little, and it has a little clip on it like an RJ45 clip does. So LC, loosened connector. And then the MTP, it's hard to see here, but the MTP has 12 individual fibers. That's why they're showing these other ends, because this cable goes around and then comes out here. There's 12 fibers on this connector. These little pins that you see sticking out, that's just a metal alignment pin. That's all it is. It just helps align it when you're plugging it in. So those are the 4 that you need to know. Okay, specifications. Focus, people. What type of connector is acceptable according to the 568 standard?
Any?
Any with what, Joel? Focus.
UL rating.
No, any connector with a focus documentation. Focus, people. Come on. Any connector with a focus documentation. FOCIS. All right. You're going to see that as a test question, so I'd write that down. Focus. FOCIS documentation. Any connector with focus documentation. What the heck are you wearing, Lucretia? Oh, it's your, oh my gosh. Okay, sorry for the distraction. Moving on. So connectors. When we connect 2 fibers together, we want to make sure we align the cores correctly. We do that with a mating adapter. So when you have different types of connectors, you want to make sure that you use a mating adapter that will align the cores correctly. Here's an example of an MPO, okay, multi-fiber connector, okay. This is the alignment pins I was talking about, here and here, okay. They go into the receiving cable over here. So an MPO, okay, with pins and receive pins. There's 12 individual fibers in between those 2 alignment pins. So that's an MPO connector. Different end polishes. Air gap, when you physically connect 2 connectors together. Flat, physical connection. A physical connection. Okay. And the APC, which is the best connector with the less reflectance.
APC.
APC. If you look at an APC cable, you can actually see the 8-degree angle. So APC connectors have to be put in just right to get that correct 8-degree angle. Okay, APC. What color is an APC connector? Anyone? Typically, what color is the connector? APC is typically green. APC is typically green. So beige is typically multi-mode. Blue is typically single mode. Green is an APC. Know those three colors. Sometimes there's other colors, but those are the three standard colors that are used. Beige multi-mode, blue single mode, green APC. Different connection termination process. We have epoxy polish, which we all did in the fiber termination class. Hot melt, this is a 3M product. So they have their special oven to heat up the connectors. And the pre-polished splice connector. I don't know if we'll have time, but I'd like for you guys to try and do one of those type of connections. So a pre-polished connector, did you guys do that in your fiber class?
I don't think so.
Where the fiber was already inside, and then you had to bring a bare fiber inside the connector, and that's it?
I think we did that, didn't we?
We did that.
Yes, we did that, Autumn. Yep.
Yeah.
But the class that you guys just certified with Steven, does Steven have you guys do it?
Yeah, Gus had us do it. We had to just cleave an end and stick it into the pre-assembled connector.
Nice, cool. What about the splice-on connector? Did you guys do that one?
Yep.
Oh, you did the splice-on connector? We actually did the fusion splicer?
Yeah.
Oh, you did do that one too. Cool.
That's the only one I think we should ever use.
Yeah, that's the only one that you should use. That's what a lot of technicians do nowadays. No, that's a fusion splice, Lucretia. Thank you for pointing that out. But I'm talking about a fusion splice-on connector. So there's actually glass sticking out of the connector, and then you splice that together.
I don't think we did that one.
Okay. I'll show it to you guys in class next week, and I'd like you guys to try it. Not everyone has to, but if it's something you want to give it a shot, you can do that. So we have the splice-on connectors. So this one you're familiar with, right? Polishing it with the polishing paper. Okay, and then using the little puck to polish it. Okay, and you crimp it on. There's the 3M hot melt. Cleaving it, polishing it. Yay, you've done all that. And then you inspect it. What type of test equipment do we use to get this imagery?
The field microscope.
Yeah, the field microscope. What are we checking for here? Good show, Silas. What are we checking for here?
I'm not sure.
See if the light's coming through.
The polish, right? Dirt. Yep, want to make sure that the core, we're going to get some light to come through, and there's no glue or debris where the core of the fiber is. Yeah, there's the 3M oven that heats up the connector. Okay, this one is what you guys did, the pre-polished splice. So here you cleave it. You can see what this, using this Corning Unicam. It's going to cleave the fiber, essentially cut the fiber at exactly the right length. And then you slide the fiber into the connector, and there's index matching gel inside the connector. The end of the ferrule of the connector, that white thing that sticks out of the connector, already has a piece of fiber that's been polished at the factory. So you're just lining that fiber, you're pushing it inside, and it's lining up. The core should line up. And then you crimp it in there to pinch it in there and hold it. The splice-on connector, this is what we have at Southwest Tech. We have this one. So this one, the connector is right here. So there's the tip of the connector. And then out the back of the connector, there's a piece of fiber already coming out. And you set it in your fusion splicer, as you can see here, and it will actually splice or weld the connection. When you do this, you then need to put down here, you can see the, this is the heat shrink tube. Okay, the heat shrink tube that has a piece of metal in it that Lucretia was showing us, that heat shrink tube slides up over the top of the fusion splice to make that more rigid and protect it. And that usually is inside the boot of the connector. All right, so permanently fusing fiber together, we are going to be using splices. So we have mechanical splicing and fusion splicing. The difference between them: the fusion splicing is 100% permanent. Okay, this is going to have the lowest loss. It uses an electric arc to fuse the fibers or melt the fibers together, where mechanical splice is similar to the splice or the pre-polished connector, and that's where there's index matching gel inside of the alignment sleeve, and then you're putting the two together. You guys did a mechanical splice before you did your fusion splice in class, I'm assuming. So here you can see a couple different fusion splicers, right? Bringing the two fiber ends together. You can visually see it in the camera. Here you can see the fiber didn't have a very clean cleave, so the fusion splicer will not splice this. Here's an example of a mechanical. So you bring one fiber in, bring another one in. You have a little visual window here. So typically you put the visual fault locator, you put light on one side, and as you come in, that light will then disappear mostly inside the other fiber as it traverses through to the other fiber, and that's what this window is for. Cleaving again is to score it and then pull, and that will usually give you a nice clean cut. Problems with splicing and connector loss. Okay, there is a test question about matching up a 62.5 and a 50 micron core multimode fibers. Okay, the cores are different sizes. You're going to get problems. Okay, mismatched core right here. So you get, when a larger core to a smaller core, you're going to get excessive loss. Okay, go in that direction. So those are different problems you're going to run across. Okay, reflectance is what happens when the light from one fiber bounces off the glass of the other fiber. So this happens on physical connectors and also on different splices. So anytime that you're joining fibers together, you're going to get reflectance. Typically, a splice has the lowest or no reflectance, but connectors have high reflectance. So here they say reflectance can be a big problem in short premises cable installations that use single mode fiber. All right, here we go into the testing, and then we will be done for the day. So fiber optic testing. The idea is we want to make sure that we test the fiber to make sure that it's going to work for the type of system that we're plugging into it. A couple different ways of doing this: visually inspecting it, and also checking for the optical power that we should be receiving, and then the amount of loss that a plant or a cable system is injecting, the fiber is causing. And then an OTDR test is the last thing we're going to be talking about, and how an OTDR test is used. So visually, we use things like a visual fault locator or a tracer. The difference between the two: visual fault locator allows you to find breaks or faults at the end that you have the visual fault locator plugged in. So you can see there's a break in the fiber somewhere in the close vicinity. Okay, if you can actually see the fiber. A fiber tracer allows you to trace the fiber line. So if you are sending light down the blue fiber in the blue tube, but on the other end, okay, on the other end at like 2 kilometers away, you see light coming out of the brown fiber in the blue tube, you now know that somebody spliced the wrong pairs. Okay, so that's what tracing is for, is to figure out, does this blue wire actually make it all the way and is it straight through? It's like doing a wire map test. Okay, so that's the difference. So visual tracer traces the fiber from one point to the other point, where a visual fault locator allows you to actually see a break in the line. So that's where you see in this third image here, you can see the light escaping out the jacket. Okay, another thing, when you test fiber for dirt and polish, you want to make sure that you make sure there's no power coming from the other end. Okay, if you accidentally take a fiber and you put it towards your eye as there's a laser going through, you're not going to visually see that laser, but your eye will still get damaged. With that brief sweep, it's not that much damage. But if you magnify that laser directly into your eye 400 times, that's when you can have long-term damage to your retina. So always make sure there's no power coming on the line. One way to do that is use the power meter. You just turn it on, plug the fiber in. If it says low, that means it's not receiving any signal. You can pull it out, and now you can inspect it with a field microscope, okay? Safety, safety, safety. Put a power meter on, make sure there's no power coming down the line, and then you can inspect it with a field microscope. This is not the proper way to clean fiber ends. Okay, that's Jimmy, by the way. That's Jimmy Hayes, who wrote, he's the author of the book that you guys used. Okay, that can actually damage the connector and actually add more dirt and problems. So that is not the proper way to clean fiber. You use a wet-dry process. So you can get wipes, you can get a spray, a lint-free cloth, alcohol. So you just get it wet and then dry it off on a lint-free cloth. That is the best way to do it. So optical power testing. So now we want to test to see how much power is on the line. This is typically done for fiber to the home installs. They are already sending power down the line because the installer is coming up to the house and going to connect the fiber, put an end on it, connect it to the equipment in the customer's house. Before they connect it to the equipment, they want to make sure that there's enough power, that they're able to actually see the signal. So they plug a power meter in and read, they should be receiving so much power from the cable plant where they're getting the internet signal from. So in order to do that, you use a power meter. Plug it in, read it, and you should be measuring dBm. That's a test question. dBm is power. That's decibels per milliwatt. Decibels per milliwatt. So where do decibels come from? Decibels are a power of ratio, power of 10. Okay, so loss, we use decibels. We identify how many decibels of loss we have. So dB is referring to loss, where in the previous slide, dBm was power. So loss is based on powers of 10. So 10 decibels of loss is actually 10 times the amount of loss. If we have 0 decibels of loss, that's only 1 time. If we have 3 decibels of loss, that's 2 times the amount of loss. So again, this is just to give you an understanding of the magnitude that it accelerates at the higher rate of loss you're going to get on a line. You're not going to see a test question on this except dB equals loss. Now down below, absolute power, we use the measurement dBm. So 0 decibels per milliwatt is 1 milliwatt of power. Negative 10 decibels is 0.1 milliwatt of power, or 100 microwatts. So test question, dBm equals power, dB equals loss. If you got that, you should be okay. Should be able to figure out the question. So the next type of test is an insertion loss test. This is what is most common for premises cabling systems. Premises cabling systems is usually within a building, linking one building to another building or one floor to another floor. So doing an insertion loss test is the easiest way to test your actual fiber optic link. What you're doing is you're simulating the actual networking equipment that is going to be plugged into the fiber. So in order to do that, you need this type of setup, an insertion loss test. This is the light source. This diagram, by the way, you need to be able to memorize this diagram. If you want, I'll give you a second and you can draw this out, but you need to be able to reproduce this diagram by identifying the different parts. So the light source, that is where the light is being generated that we're going to try and measure. That's the same thing as the transmitter in the fiber optic link. So that equipment is going to transmit light. We need a reference cable, a launch reference cable. This is the reference cables that are in our test kits on campus. So these are the cables that we have, that we bought from the factory, that are known good cables. So we have the launch cable. Then we have the fiber plant that we're actually testing. So here we're testing a cable, or we could be testing the fiber plant that we have installed in the building. And then at the other end, in the other building or the other floor, we have the receive cable, the receive reference cable, which again is a factory made cable that we purchased, plugged into the device that's going to read the amount of loss. That is the meter, the power meter. So identify all of these components, these 5 components you should be able to identify. Giving you guys a second to draw that out if you want to in your notes. Again, physically drawing it out is going to help you mentally retain that and recall it. So an insertion loss test. Okay, this is going to test. We need to make sure that we match the proper connector, okay, the mating adapter. Make sure that we use the proper fiber size. Okay, these reference cables, if we're testing multi-mode fiber, the launch cable and the receive cable should also be the exact same multi-mode fiber. So if we're testing 62.5 multi-mode fiber, these launch and reference and receive cables should also be 62.5 core. If we're testing OM3 multi-mode, we need to make sure our launch and receive cable are OM3 fiber optic cable. So you got to match the fiber type, the size, and the connectors. Okay. We also need to make sure that we are transmitting an LED or a laser at a certain wavelength that the actual system is going to be working at. So if we have equipment in my network that is going to be transmitting 850 nanometers, then that is what I need to test, 850 nanometers. Even though 1310 or 1300 is going to give me a better reading, I want to test the same wavelength that my equipment is going to be transmitting when my customer turns on their networking equipment. So here's an ultimate question. How do I set a reference? Because what I want to do is measure the amount of loss that my cable plant has. So how do I set reference between the source and the meter?
Don't have a test cable.
Well, we're going to use, no, before I plug a test cable in, Silas, before I plug this cable in, what do I do between the source and the meter? Remember, you pushed a button and you held it?
You offset the 2 reference cables.
Yeah.
Yes, you zero out. So you make these reference cables that are plugged in, you plug them into each other, and then you zero them out, making those reference cables disappear. They're not part of the reading any longer. So now the meter will only show the cable that you plug in here, Silas. Okay, so the patch cable you're testing or the fiber plant that you're testing. So you will be doing this test for your hands-on. So the fiber portion of your hands-on exam is going to be testing the already installed fiber. So I've already installed the fiber in those 4-post rack enclosures. You need to test and make sure that what I did is what is expected. And if there are any problems, you need to identify what the problem is and what you would do to repair it. I don't want you to repair it because I need them broken for the next class. I want you to identify what the problem is and which pairs, or not which pairs, but which fibers, and what you would do to repair it. So, testing the cable plant or patch cord. Okay, the patch cord test. This is a test question. FOTP 171 is a patch cord test. You only need one reference cable. Okay, that is a perfect test to test FOTP 171, one patch cord. One patch cord, one reference cable, one patch cord, one reference cable. FOTP 171 is a perfect test for patch cords. One reference cable, one patch cord. The cable plant, though, you've got two ends. You've got the end in the data center, you got the end in the computer room, and you got the end in the telecom closet. Okay, you're testing both ends, double-ended. Okay, OFSTP, 7 for single mode, 14 for multi-mode. OFSTP is the double-ended test to test the cable plant because you have two ends. This floor to this floor, you got to test. 7 is smaller, 14 is larger. 7 is single mode, 14 multi-mode. These are test questions, people. Write them down. OFSTP, 7 single mode, 14 multi-mode. Cable plant test. FOTP 171 is a patch cord test. Patch cord testing, FOTP, oh, there's a typo, gotta fix that, is one reference cable to test one patch cord. When you are testing this, you zero it out. You plug the source reference cable into the meter, hit 0, then plug in your patch cord, and then you're testing the patch cord. This is another tip for you. You can figure out which connector has the worst amount of scratches or dirt or reflectance. So if you test this patch cord, you plug one end in here and plug one end in here. If the light hits this connector and is not able to transmit, you're going to get a low or a high amount of loss, right? So you're going to get a high loss. But if you flip this, put this connector down here and this connector up here closest to the source, more light will pass through the cable, getting closer to the meter, and you'll have less loss. So now you know the first direction that you tested it, you have the most loss on that connector. Cable plant, OFSTP 14 and OFSTP 7 uses two double-ended, two reference cables. And again, you plug in the reference cables to each other, zero it out, and now the cable plant that you're testing is the everything in between those two ends, those double ends. So 0 decibel reference. You have a single cable, double cables, or 3 cables. The whole idea of the 3 cable test is you have a golden reference cable. This cable that was made in the factory allows you to calibrate your testers. Okay, that's the only purpose of that. But you only need to know these 2 options. The FOTP 171, using 1 cable for testing a patch cord, 2 cables, double-ended. OFSTP 14 is multi-mode. OFSTP 7 is single mode. We use the double-ended test for cable plants. Okay, other issues that you'll run across, snap problems when you're testing fiber, is the quality and the connection of the reference cables. Make sure your reference cables are clean. Okay, clean them off. A little bit of alcohol, a little bit dry them off, and then use them. Even though you pull them out of a plastic bag, who knows who put them in there. Okay, make sure that with multi-mode fiber, you might have modal dispersion, which means that you might need to use a coiled multi-mode, and that just settles down the light being sent in that short distance. You're probably not going to get a test question on that, so you should be okay. But setting the proper 0 decibel reference, okay, maybe you didn't zero it out. Another tip is keep the light source and the meter and the fiber that you're using, keep it still. Set it on a table somewhere. Don't touch it. Okay, the more you wiggle the fiber or bend the fiber, your reading is going to go up and down. So multi-mode dispersion. This is what happens is the short distance. Okay, you're going to get different densities of light, and you're going to get problems with this. So the idea is you essentially take fiber, multi-mode fiber, and you wrap it around a certain diameter of a hard pipe, essentially. You can actually purchase special things for this. So it's called a mandrel wrap. Okay, so you take multi-mode fiber. You only do this for multi-mode fiber for short runs. You run the fiber around this mandrel, and the mandrel is a certain size diameter, and then you test it. So that settles down the light, essentially. You don't have to know anything except this multi-mode fiber will sometimes need a mandrel wrap. That's what this is referring to. A mandrel wrap is used for multi-mode fiber testing. All right, the last test that you will see test questions on is an OTDR test for fiber. An OTDR is a single-ended test. Means that you can test it without having to run the light source or the power meter on one end of the cable and then run the meter to the other end of the cable. You can just, from one end, you can do a test, and it sends the light down the fiber link, and then it measures the backscatter, meaning it measures the reflectance of each event back. So it's very sensitive, very expensive equipment. Okay, it takes a snapshot. It makes a picture of what the fiber actually looks like. So OTDR, this backscatter, right? This amount of light reflecting back, it records those different events. It's going to measure distance because of how long it takes for the light to get down and how long it takes for the reflectance to bounce back. It's going to measure loss. Okay, how strong is that light that's coming back? It's going to measure where there is a connector and where there is a splice. It does not measure insertion loss. It does not measure insertion loss. It estimates loss based on the reflectance. So this diagram on the bottom here is what you're going to need to be able to identify for the test. we have the X and Y axis. The Y axis is going to measure the amount of loss. Going to measure the decibels of loss. The X axis is going to measure the distance that your fiber runs and at what point is a connector or splice at that particular point. So the X and Y axis. Know which one measures loss, which one measures distance. The initial pulse and dead zone. This is referred to as your launch cable. Okay, this occurs at the launch cable. So the beginning of your cable plant that you're testing is at the end of the dead zone. Okay, the initial pulse is the initial high power light that's being transmitted down, and that is a launch cable. That launch cable, where that ends, that's where your cable plant begins, and now you're measuring the distance, okay, to the first event. The first event here happens to be a reflectance. That's where we see the spike. Okay, that reflectance, and then an immediate loss. Okay, so that is going to measure the amount of loss right here that this connector is injecting into this cable plant. And if you go down here, that'll be the distance that that connector is. So if we have a connector at about 1,000 kilometers, I'm sorry, that's a lot, at about 1,000 meters away or 1 kilometer, okay, that's where the connector is. When we do an OTDR test, we should see 1 kilometer, and that's where this reflectance should occur. Moving down the line, we see we have more loss because of the length of cable. Whoop. And we see a splice. When we see an immediate drop and little to no reflectance, that is referred to as a splice, not a connector. And then we see a bunch of noise at the end. That is considered end of the fiber. So all of this noise at the end here, that's the end of the fiber right there. So again, let's take a quick review on all of these things. This diagram, you're going to be able to need to identify each one of those. So when we are testing and taking a look at the OTDR trace, the slope is going to measure two things. This slope is measuring distance and loss. So here I'm measuring loss over distance. This connector here, the marker from this point right here, where my mouse is, to where the slope starts to go down again, that is the amount of loss that that connector is injecting into our plant. So measuring from this point to this point is the amount of loss the connector is injecting. Over here, if I measure the beginning of this slope here and the end of the slope here, that is measuring the amount of loss that that splice is injecting. So these are the markers that I'm referring to. So if you have a red marker here and a red marker here, this, you're measuring the distance between the two markers, and you're also measuring the amount of loss that that distance of fiber has in our cable plant. When you put the red marker right before the slope and then right at the end where the slope starts to even out, you're measuring a splice loss. You're measuring just the loss. Now, on this one, we put the marker right where the slope starts to rise, and at the very peak, what you're measuring here is the amount of reflectance that that connector is injecting into your plant. You're not measuring the loss. That would be way down here. Okay, similar to this one. You measure from this point to this point, that would give you the loss. In this example, in the bottom image, you're recording the reflectance, the amount of reflectance that is happening in that connection with that connector. Okay, so doing an OTDR trace is not as easy as just plugging it in and hitting start. You have to actually set up different readings. You have to identify how long is my reference cable? How long is my launch cable? How long is the cable that we're testing? I think it should be 5 kilometers long. So you need to make sure you set the OTDR to assume that it's going to be transmitting at least 5 kilometers. You have to set other things on how many samples it sends, okay, and how frequent it sends those. So it actually sends millions of light pulses down and receives millions of those back. It goes ding, 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 and it receives those back. Every single one it records. And then it averages them out, and those are the numbers that you show. So it does multiple tests. Some errors that you can get using an OTDR, okay? So when we're measuring from this point to this point, that's the actual loss that you get in that splice. Okay, sometimes you'll get a weird measurement where that line actually stops, it disappears. And that just comes with the math of trying to average those numbers out of all of those tests. Okay, some of those don't get recorded because of the distance of the cable. So sometimes you'll have weird little breaks like this one, or you'll have what looks like a gain. It's called a gainer. Okay, either way, you measure the distance between the two, and that gives you your measured loss. So you measure the gain from here to here, and that gives you your actual loss. So it's kind of weird, but that's what happens. Another thing you'll see is if you see an exact duplicate, okay, see this? If you see an exact duplicate, that's called a ghost. Ghosting is not when you ignore somebody on direct messaging or social media. Ghosting is what happens when you have a short fiber cable being tested with an OTDR, and it's too short that the reflectance that's coming back, it's recording it twice. So that's called a ghost. Multiple reflections. So you got to be careful. That's another problem you can get. So here's an actual OTDR trace. This is what it looks like. This is a beautiful trace. And some things you can read on here, okay, is line 1, okay, and the distance that they're at. So here you can see connector 1, the first connector. This first connector is where the launch cable is. Okay, so from here, I don't know if it's easier to see in this image down here. That marker is kind of right up against the edge here. It's hard to see in this picture. But that marker is right here. And then all the way over here, this marker here that you can see going up and down is the second marker. So that is, so line 2, which this is line 2, is at 1 kilometer away. So from here to here is 1 kilometer of fiber. So it looks like at about 500 meters or half a kilometer, there's another connector. So we have about 250 kilometer patch cord in between there. That 250 kilometer patch cord, we have the two connectors connecting it. And then we have the fiber that goes underground probably. And there's a tiny bit of reflectance. That's a splice. And then we go down, down, down the fiber, and we get loss all the way to the point where we see the last connector. Okay, you see the reflectance, and then all of a sudden it drops and there's just noise. That's the end of the cable. That's the connector on the end. So in this 1 kilometer, can anybody tell me, in 1 kilometer, how many decibels of loss is that 1 kilometer with those two connectors injecting into this OTDR trace? What is the reading? Can you see that number in the window?
2.109.
Yeah. Was that Austin? Good show, Austin. Right here is where he read that. So in that 1 kilometer, these two markers are measuring, we have 2.109 decibels of loss. Cool. So that's where you see all of the different measurements for the markers. So in this example, we have marker 1 here, the second marker here. We're measuring distance and we're measuring the amount of loss over that distance. So in this reading, it's 9.25 decibels of loss, but that's over 3 kilometers right before the splice. So we have a 3 kilometer fiber run. That 3 kilometers of fiber, we're losing 9.25 decibels of power. Next, safety. Read and follow all the rules about working with fiber, policies that your company has. Number 1, wear safety glasses. Also dispose of fiber scraps carefully. Okay, bad problems, hemorrhaging, and eye loss can occur with fiber scraps. Careful with chemicals, alcohol, cleaners, especially when you're using fusion splicers, creating electric arc. And no eating or drinking, Andrew, when you're working with fiber, right? All right, that's it. You guys did it. So there will be a quiz I'm going to activate as soon as I end this call. I will put this recording up on Schoology as well. So if you need to go back and review any part of it, you can. Please complete the quiz on Schoology before next Monday. I will see you on campus next Monday for your morning session, people, or afternoon session, people. Keep your fingers crossed. There's no water main breaks.
Do you think that campus is going to be open tomorrow?
With the water main break, I think so.
Okay.